Welcome to a deep dive into two fundamental concepts in low-level engineering: processes versus threads. The choice between them isn't merely academic. It boils down to a critical engineering dilemma. How do we balance isolation and stability against raw performance and system complexity? At its heart, this isn't about philosophical debates, but about the tangible realities of CPU cycles, memory pages, and the brutal, often frustrating, reality of debugging. We're constantly navigating the tension between keeping components separate and making them work together efficiently. Let's start with processes. When you opt for multiple processes, you're essentially spinning up entirely separate, ironclad execution environments. Think of them as distinct virtual machines, each completely isolated from the others. Each process comes with its own dedicated address space, its own set of register file contexts, and its own file handles. The operating system's memory management unit, or MMU, acts as a strict bouncer, enforcing these boundaries. One process simply cannot directly peek into another's memory without explicit, OS-mediated inter-process communication. The core problem processes solve is system stability and fault isolation. If one process crashes, perhaps due to a rogue pointer, its blast radius is contained. The kernel cleans up and other processes continue unaffected. This is precisely why modern web browsers often assign each tab its own process. A catastrophic bug in one tab won't bring down your entire browsing session. But this isolation comes with trade-offs. Firstly, memory overhead. Each process demands its own complete stack, heap, and code segments. While copy-on-write can optimize initial sharing, any write incurs a full copy. Secondly, inter-process communication, or IPC, is slow. It requires system calls, kernel involvement, and often data serialization, akin to sending data over a network, not directly accessing memory. Another significant cost is context switching. Switching between processes is a heavyweight operation. The OS has to save the entire state of the current process and then load the entire state of the next. This incurs a measurable CPU cost, impacting overall performance. In contrast, threads operate on a fundamentally different principle: shared memory. Multiple threads within a single process share the same address space, the same global variables, and the same heap. Each thread primarily gets its own execution stack and a set of CPU registers. The technical problem threads address is the need for fine-grained concurrency and efficient data sharing for closely related tasks. When multiple parts of your application need to operate on the same complex data structures, copying this data between processes would be prohibitively expensive. Threads allow direct, immediate access to this shared state, leading to higher performance. But this power comes with immense responsibility. Shared memory means you're exposed to a gauntlet of complexity. We're talking about race conditions, where multiple threads corrupt data; deadlocks, where threads wait indefinitely for each other; livelocks, where they constantly change state without progress; and even subtle cache coherency issues like false sharing. Diagnosing these issues is notoriously difficult. We call it debugging hell. The non-deterministic nature of thread scheduling means bugs might only appear under specific, hard-to-reproduce timing conditions. Every function and data structure interacting with shared state must be meticulously designed to be thread-safe, often requiring synchronization primitives like mutexes or semaphores. So, what's the pragmatic choice? It pivots entirely on the specific problem you're solving. If modularity, fault isolation, and resilience are paramount, where component failure cannot cascade, processes are your robust, albeit more resource-intensive, choice. However, if you're tackling compute-bound tasks, need to leverage multiple CPU cores efficiently on large, shared datasets, and prioritize raw performance, then threads offer the direct route. But be warned, mastering threads requires a deep understanding of concurrent programming, and it's where you truly earn your engineering stripes.